So what you're seeing here is an absurdly powerful magnet, and I have a wire lying on top of it. In a moment, I'm going to momentarily run a ridiculously large current through this wire. Let's see what happens. And let's try it again. Okay, so you can see that whenever I run the current, apparently the wire is feeling a magnetic force. Now it goes without saying, don't attempt to recreate this one. Large currents aren't exactly a safe thing to do if you haven't been properly trained. And the magnet that I'm using here can really pinch you good if you aren't handling it correctly. So what was going on with that demo? Well, you had electric charges that were moving through a magnetic field. Just this time, they happen to be moving through a wire. So let's go ahead and draw a wire. And since we saw, looking at the Hall effect, that the magnetic force will be the same regardless of whether we're talking positive charges flowing to the right or negative charges flowing to the left, let's just go ahead and think about a conventional current that's going to the right. And for our purposes here, we can think about a small period of time where we will be having a small batch of charge here. We'll call this delta Q. That is drifting to the right because I'll go ahead and assume delta Q positive. And all of this still works if we assume delta Q to be negative with the drift velocity to the left, as we saw when we looked at the Hall effect. So we can follow this thought through here. We have, and let's also, while we're at it, we will dimension our wire. Pardon me a second here. So let's go ahead and dimension our wire to be L. And we're eventually going to turn L into a vector, and so I'll make it point in the same direction as the current. And also let's go ahead and draw in the magnetic field passing through the wire, making some angle phi with respect to the current and, for that matter, L. All right, so we can start by saying that the force that the wire would feel would be equal to QV cross B. Now, here's the trick that we can do. If we go ahead and take a look at the time it takes for this piece of charge here to move across this length L, we can observe that L will be equal to V delta T. So I can go ahead and multiply and divide through by L. So this would give me our parcel of charge delta Q over delta T. And then we will have V times delta T, and all that crossed with B. But now this is going to be L, and this is our current. So the magnetic force acting on a wire turns out to be equal to IL cross B, where L is the length of the wire pointing in the direction of the conventional current. So when we were taking a look at this in the demo, the wire was carrying a current, the magnetic field was coming out of the screen at you, and so the force would be at right angles to both the current and the field, which is why you saw the wire deflect sideways. So let's go ahead and do an example of this, and I am going to make what amounts to the world's worst motor, because it isn't even really a motor. Let's imagine that we've got two very long conducting rails, like so. And we're going ahead and pulling a current, or well, we have the potential of having a current go through. We'll go ahead and hook up a battery with some load just to make sure that we don't have ridiculous currents that burn everything down. Safety first. Let's say, for sake of argument, that the spacing between the rails is 0.5 meters. And now what I'm going to do is I'm going to have a conducting bar that is free to slide on top of the rails. So let's go ahead and have a magnetic field that is pointing into the screen. Like so. And let's say its strength is 1/10 of a Tesla. We'll initially have our rail sitting at a halt. So we'll say V initial is equal to 0. So the way I have this drawn is we've made a connection now. So is there going to be a current flowing clockwise or counterclockwise through the circuit? Yeah, the current will be flowing clockwise because this is the positive terminal of the battery, so the current will be going around like this. So that means within the bar we will have a current pointing down. Let's go ahead and assume this is all rigged up so it's 1 amp. And let's also go ahead and stipulate that the mass of my bar is 2 kilograms. Now let's go ahead and let it, first off, figure out which way is it going to feel a magnetic force. So go ahead, do the right hand rule, pause the video, and come back with me. Right, so we should be putting the index finger of our right hand along the current here pointing down. You turn your hand around that index finger until your field fingers are going into the screen. When you do that, you'll find that your right thumb is pointing to the right. So we're going to feel a magnetic force to the right. That means the bar is going to accelerate to the right. So let's go ahead and think about the bar once it's traveled 1 meter. Let's go ahead and figure out how fast it's going at the end. Okay, so this harkens back to doing mechanics. And we look at this and realize that this is a kinematics problem, except that you're missing 2 of the kinematic variables and you're only allowed to be missing 1. You don't have the time, and you also don't have the acceleration. So then the idea is going to be, well, but we can buy ourselves the acceleration from Newton's second law. So first, let's just go ahead and set up the kinematics here. So in the x direction, we will pick the missing t equation that says v final squared equals v initial squared plus 2a delta x. And remember, this is called missing t because time doesn't show up anywhere in this kinematics equation. So we can go ahead and solve it. So we can go ahead and put in that v initial is 0. And so we can solve that v final is the square root of 2a delta x. So we now just have to come up with an expression for the acceleration, but we can get that from Newton's second law. A is going to be equal to the net force over the mass. In this case, the only force we have is the magnetic force. Now, we need to take the magnitude, and since this is a cross product, it'll be equal to I times L times B times the sine of the angle between, sine of the angle between I and B. So I is going straight down and B is going straight into the screen, so that's a right angle. So we can go ahead and write that this is ILB sine of 90 degrees over M. The sine of 90 is 1. So we can take that and substitute into V final. So V final, final will be equal to the square root of 2 ILB delta x over M. So let's just go ahead and put in our values. So this will be 2 times the 1 amp current. We said the length of our bar here, or the relevant length, that's an electrical contact, is 1/2 meter, the spacing between the rails. We said that the magnetic field strength was 1/10 of a Tesla, and that the bar moved for 1 meter, and its mass was 2 kilograms. Now you crunch all this through and you find that your bar is now moving at 0.224 meters per second. So, I mean, it's pretty respectable, 22 centimeters a second. That's moving on pretty good. Now, in practice, you would never try to build a motor like this because in order to keep getting useful work out of it, you would keep having to have more and more and more conducting rail. The thing would have to be infinitely long. So we will be working our way towards figuring out how to make a useful motor out of it in just a bit. But first, I would like to make a bit of a detour, and I would like to revisit the definition of the ampere. So this is the previous definition. Of the ampere. So this is before the revision to the SI system that occurred in 2019. In that definition, in that version, the ampere was defined by thinking about 2 infinitely long wires that were spaced a meter apart. So we'll just say we'll call the separation D. Let's say it's 1 meter. So we'll have to think about some chunk of the wire of length L, but that won't matter. We'll be dividing it out. So in the thought experiment, the wires are set up to have identical currents, but I'm just going to call them I1 and I2 just so we can keep them straight. So you have a so if we want to find the magnetic force on I2 due to the current flowing through I1, remember that I1 is making a magnetic field in the region of I2. So the magnetic field, following the hitchhiker rule, we put our right thumb along this current here, And we get that the magnetic field lines are circles going around the wire. So to the left of the wire, the circles will be pointing out of the page, out of the screen. And to the right of the wire, they will be pointing into the screen, like so. And of particular interest will be the magnetic field lines due to wire 1 out at the location here at wire 2. So this is the magnetic field due to wire 1 over at wire 2. Like I said, remember the magnetic field lines themselves are circles. We're just looking at where they pop out of the page. They'll loop around to the front of the wire, go into the screen here, loop around behind the wire, and so forth. So right at this location here, the magnetic field due to wire number 1 at the location of wire number 2 is pointing into the screen. So I want you to go ahead and do the right-hand rule again here to figure out the direction of the force that wire 2 will feel from wire 1. Okay, so you should be taking your right hand, putting your index finger to be pointing up. Turn your hand around your index finger until your field fingers point into the screen, and you should find that your right thumb is pointing to the left. And so this is the force on wire number 2 due to wire number 1. I will leave it as an exercise for you to see that the direction is equal and opposite here, that the force that wire 1 feels due to wire 2 points in opposite directions, and we'll see equality in a second here, or I'll leave that as an exercise too. So let's go ahead and calculate this F2 on 1, which I promise you is the same as F1 on 2, so I'm just going to call it F. Well, it's going to be equal to ILB sine, and again here the angle that we have between the current and the magnetic field is 90 degrees. The current is pointing up the screen, the magnetic field is pointing into the screen. That's 90 degrees. The sine of 90 is 1. So this is the current number 2, and this is magnetic field at location 1. But we remember that the magnetic field due to this wire was equal to mu naught. Sorry, let me just call this L like so, just to be consistent. There we go. Was equal to mu naught I, 1 in this case, over 2 pi times the distance you are away from the wire, in this case D. In the equation when I wrote it before, that was an R. Okay, so we can rearrange this to get it into standard form. This would be mu naught L I1 I2 over 2 pi D. I'll leave it as an exercise for you to do the equivalent thing for F12 to see that you get exactly the same result respecting Newton's third law of motion. Now, in this thought experiment that was used to define the ampere, you would make I1 equal I2. And what you would require was that the force per unit length, so dividing through by L, so this would be equal to mu naught I squared over 2 pi D. If D was 1 meter, you required that the force per length that you had was exactly 2 times 10 to the negative 7 newtons per meter. And this defined the current to be 1 amp. So under these conditions, the current is defined to be 1 amp. The triple equals sign means by definition. And so, believe it or not, for as unwieldy as this seems, and you're thinking, how could I ever build a lab practical version of this? Well, there's a way where you could bootstrap it from this thought experiment into lab practical comparable experiments. And that was how the ampere was defined. And believe it or not, the coulomb was the derived unit. The ampere is the base unit. And so the coulomb was defined to be 1 amp times 1 second. So a coulomb was the amount of charge that would flow by some location in 1 second if you had a current of 1 amp. With the redefinition, this has been kind of turned on its head. So the current definition so this is the post 2019 definition of the ampere. Remember, in the redefinition of the SI unit system that occurred in 2019, all units are defined implicitly by setting certain physical constants to be equal to exact values. So in the current definition, what has been done is the fundamental quantum of charge is now defined to be exactly 1.602176634 times 10 to the negative 19, you guessed it, amp seconds. They still don't want to say coulombs because in order to provide back compatibility, they keep the ampere as the base unit and define the coulomb still as a derived unit of 1 amp second. So this is an exact value. And it's still the case that the derived unit, very technically at this point, is that the coulomb is still 1 amp times 1 second. But here that's almost becoming a difference without a distinction without a difference, because we would normally just write coulomb here. We always do. But the very, very fussy definition is to call that an amp second in order to define the amp and then say, oh, the coulomb is an amp second. Now let's go ahead and call it a coulomb. Again, that's purely to provide back compatibility with the previous definition. All right, so I've been promising trying to get us a little closer to building a half-decent motor. So let's start to think about the torque on a magnetic dipole. So what I'm drawing here is I'm imagining that this is a square loop of wire. And you are looking at this loop edge on. Let's say that the current that we are carrying through the wire is coming out of the top part of the square that you're seeing edge on here. It'll flow down like this, go in, and then on the back part of the square, which is covered up by this, it'll flow back up again to complete the square around. So this is a side view of a square of wire. If it helps, just take like an index card or something like that. hold it to match what I've drawn edge on, and then you can imagine the wire as having been wound around the perimeter of the index card. Okay, so if you follow your thumb along the current going around this perimeter here, you'll see that the fingers of your right hand will point like this going through the inside of it. And so as we've seen with magnetic moments before, this means we've got our magnetic moment pointing like that. Let's go ahead and have an external magnetic field going through this whole contraption. And we will say that the angle that we make is the angle between the magnetic moment and the magnetic field. So not between the coil and the field, but between the magnetic moment and the field, which is the complement of that other angle. Okay, so go ahead and do some right-hand rule action and figure out the directions of the magnetic forces on the top and the bottom part of the windings here. Okay, so for this one, you should be pointing the index finger of your right hand out of the screen. Rotate your hand around your index finger until your field fingers point to the right. That might start to take a little bit of gymnastics to make it happen, but you can make it happen. The magnetic force here is pointing up. And similarly here, it's pointing down. And these are equal because the current is the same and it's a square loop. So we'll just go ahead and say that this is a square loop that is of length L on a side. All right, so from this we can start to figure out the torque that we would be feeling here. If I go ahead and drop down a line of action for my forces here, like so, like that, we can see here that our perpendicular here, well, if this angle's phi, so is that angle there, and so is that one. So our perpendicular here and also our perpendicular there will be equal to L over 2 sine phi. The reason it's L over 2 is the hypotenuse I'm using is half the length of the wire here. So this distance right here is L over 2. All right. So we have, so our torque, well, we have two contributions, one due to the force here, one due to the force there. 2 times the magnetic force times the lever arm, and this is just because we have 2 contributions. And then we can go ahead and put in for this. So this will be 2. This will be ILB. And again here, the current is either going straight in or straight out of the screen. The magnetic field is pointing in the plane of the screen. So this is again going to be a sine of 90 degrees, which is 1. And then our R perpendicular is L over 2 sine phi. So the 2's cancel, thank God for small favors. And we can clean this up just a little bit to get that this is I times L squared B sine phi. Now this L squared is the area of the loop. Now, although I did this for a square loop, it turns out to be true just plain in general, regardless of the shape of the loop. But in any event, we can look at this and realize that this is our magnetic moment that we've seen before. And because we've got a sign phi here, we're definitely thinking cross product. So remember, when we're doing torques in 3D, if a torque is trying to make something twist counterclockwise, the vector arrow we assign to that torque points out of the screen. And it's trying to make it twist clockwise, it points into the screen. So we need the torque to point into the screen here. So let's just go ahead and note that, like so. So we need the torque to point into the screen. So now we need to figure out, is that mu cross b or b cross mu? Go ahead and do the cross products each way, and you tell me what you get. Okay, so if we follow the first things first, second things second way of doing cross products, the way that you do this to get the torque to point into the screen is if the mu went on the index finger and b here went on the middle finger. So this means that we can write this in vector form as the torque on a magnetic dipole is equal to mu cross b. So what does that mean in practice? What that means in practice is that the torque is always seeking to align the magnetic moment with the magnetic field. So the trick with a motor is right at the split second that the magnetic moment aligns with the magnetic field, you flip the direction of the current going through the windings. This is usually done using a device called a commutator, if it's a DC motor. And so when you flip the direction of the magnetic moment, now once again, you're going to be exerting a magnetic torque to try to align it. And then again, you rig it up so that at the instant it's aligned, you flip the direction of the current, which flips the magnetic moment. And so it keeps endlessly applying a torque on the loop to make it turn around. And that way we can do useful work and make cars go down roads and stuff like that. Alrighty, so in the next video, we will take a look at what's happening on the atomic scale for us to have permanent magnets. And yeah, so we'll take a look at that there. Catch you in the next one.